Chapter 5, Section 3 is about magnetic force. First, let's remember some points from grade 11. Let's have electric field, one side as positive, one side as negative, and you'll have an electric field from positive side to negative side. Let us have a charge, a positive charge, that is at rest, so velocity is equal to 0. And you will insert this positive charge into an electric field, and let's see what happens. We will see that it will directly start to move toward the negative part because there will be an electric force acting on it to the right side. And if we have an electron, again, that is at rest, as soon as we insert it in the electric field, it will start to move because of the electric force. The question is, what happens if we put these charges inside a magnetic field? Will there be a magnetic force acting on them? Let's have a magnetic field, and we will put the same charge that is at rest inside this magnetic field. So will there be a magnetic force acting on it? Right now we will see the charge will not start to move, which means that there is no magnetic force acting on it at all. So magnetic force will be equal to 0. So the charge must be moving. Let's have a moving charge then. Let's say that we have a charge that is moving to the right side. The magnetic field is also to the right. Let this be a positive charge. Will there be a magnetic force acting on it? Again, the answer is no. Magnetic force again is equal to 0 because the velocity of the charge is parallel to the magnetic field. So the charge must be moving perpendicularly to the magnetic field so that there is a magnetic force. Let's have the third example. A charge that's moving perpendicularly to the magnetic field, and as you see, velocity and magnetic field are perpendicular to each other. Right now the magnetic force will be maximum, which is equal to Q, the magnitude of the charge, multiplied by the velocity multiplied by the magnetic field, will give us the maximum magnetic force. For the fourth case, what happens if the velocity is at an angle with magnetic field of the velocity, and the angle is between the magnetic field and the velocity. The velocity will have two components, a component that is parallel, a component that is perpendicular. The component that is attached to theta is cosine, and the one that is not attached is called as sine theta. So we will see that the cosine component is the parallel component and the sine component is the perpendicular component. So we talked about that one a moment ago. So you'll have a magnetic force because of the perpendicular component, and there will be no magnetic force because of the parallel component. So the equation for the magnetic force becomes QVB sine theta, where theta is between the magnetic field and the velocity. The unit of magnetic force is Newton, the unit of charge is Coulomb, and unit of velocity is meter per second, and the magnetic field is Tesla. Let us rearrange this. Tesla will be equal to Newton times second divided by Coulomb times meter, or Coulomb per second is ampere, and we can rewrite Tesla as Newton over ampere times meter. Remember that this equation is correct for a charge that is moving in a magnetic field. Equation only gives us the magnitude, but magnetic force is a vector quantity, so it has direction too. So what should you do about direction? We have to use a new right hand rule to find direction of the magnetic force, which is called as, I'm calling it as straight right hand rule, because this time, unlike the previous one, your forefingers will be straight, it will not be curled. So whenever you see magnetic force and direction in a question, always use the straight right hand rule. Please do not curl your right hand, so you have to use right hand again. First, remember that magnetic force is perpendicular to the magnetic field. It is also perpendicular to the velocity. So we have three quantities, so we need to have three locations on our right hand. The first one is the thumb, which will be the velocity. The second one is the forefingers, which is the magnetic field. And lastly, it is the palm, which will show as the magnetic force. But the magnetic force acting on a positive charge is opposite to the magnetic force acting on a negative charge. The palm of the right hand will be used for positive charge, and the back of the right hand will be used for negative charge. Can we use our left hand for negative charge? Yes, you can use the palm of your left hand for the negative charge. Let's have a magnetic field that is into the page, a positive charge that is moving up to the page. The magnetic field is into the page, which will be our four fingers. So our four fingers will be into the page, and our thumb will be up to the page, which is the velocity. Automatically, our palm will face the left side, which is the magnetic force. From chapter 1, we already know that if a force is parallel to a velocity, it will change speed. It is either increasing or decreasing the speed depending on their direction. If a force is perpendicular to a velocity, it will change direction, which we had in circular motion. So here we will have a circular motion because the magnetic force is changing the direction of the velocity, and it will change the direction of the velocity always toward itself. For example, in this particular picture that we had a moment ago, the force is to the left side, so it will change the direction of the velocity toward the left side until the charge will be moving to the left. At this point, if we use the right hand rule again, our four fingers into the page and thumb to the left, our palm will be facing downward, which shows that the magnetic force is this time downward. Again, it will change the direction of the velocity toward downward this time until the direction of the velocity becomes downward. At this moment, if we use the right hand rule again, we will see that the palm is to the right side this time, and it will change the direction of the velocity toward the right side until the velocity becomes toward the right side. And at this point, if we use the right hand rule, it will be up to the page, and we see that it will change the direction of the velocity to up this time. And it has completed a circle, so it follows a circular path. So we can say that if a charge enters a magnetic field perpendicularly, it will follow a circular path. Since we have a circular path, it means we have centripetal force, and the force that is always toward the center is already the magnetic force. This magnetic force always toward the center. We can say that centripetal force is equal to magnetic force. Centripetal force is equal to MAC. Magnetic force is equal to QVB sine theta, but we don't write the sine theta because the velocity is perpendicular already. So sine theta is 1 here. MAC will be equal to QVB. What happens if the charge enters the field at an angle this time? This is the magnetic field, and this is the velocity. And the velocity will have two components, a component that's parallel to the field. I will be calling this as parallel component, and this one as perpendicular component. Because of which one do we have magnetic force? Because of the perpendicular component. There will be a magnetic force acting on the perpendicular component. So the perpendicular component will follow a circular path, but the parallel component will have no magnetic force acting on it. The parallel component will move in a straight line, and they both are happening at the same time. We'll combine it, and you'll see that the charge will follow a helical path. The charge, if the magnetic field was into the page, the path was counterclockwise. So if I make the charge as negative, the magnetic field is still into the page, the path will be reversed, which will become clockwise. This time I will have the charge as negative. I will not change the charge, but I will be reversing the magnetic field, which is out of the page, and I will see that the path will be reversed again, which becomes counterclockwise. This time I will have the field same as out of the page, but I will reverse the charge, which becomes positive. If I reverse the charge, the path will be reversed, which becomes clockwise. We said that if a charge moves inside a magnetic field perpendicularly, there will be a magnetic force acting on this charge. And we remember that current is the movement of charge in a time interval, and current has the same direction as positive charge and opposite direction as the negative charge. So if we have a wire that is carrying a current inside the magnetic field, it means that the charges are moving, and since the current is perpendicular, the velocity of the charge will also be perpendicular. So as a result, there will be a magnetic force acting on every charge, and when we add all of them, there will be a magnetic force acting on the wire too. Let's have a wire that's carrying a current to the right side that is inside the magnetic field. which is into the page. This wire has a length. Why would the length be important, you would ask? Because if we increase the length of the wire, the number of the charges that are moving will also increase, which will increase the magnetic force acting on the wire. So we can say that magnetic force acting on a wire is equal to magnetic field, but this magnetic field is an external magnetic field, please remember that, multiplied by the current, multiplied by the length of the wire, and if we have an angle, multiplied by sine theta. This is the equation for magnetic force acting on a current carrying wire inside a magnetic field. Equation always shows as the magnitude, but to find direction we need to use a right hand rule. Again, we will be using the straight right hand rule, but this time the thumb will be the current. Actually, it makes sense because the current will be in the same direction as the velocity of the positive charge. So you can consider current as velocity too, and it will be the thumb. And the four fingers that are straight will be again the magnetic field, and the palm this time will be the magnetic force. Since the current is the direction of the positive charge, we only need the palm. Please remember this magnetic field is the external magnetic field. So force is Newton, magnetic field is Tesla, and the current is ampere, and the length is meter. When we rearrange this, we will get Tesla, that's equal to Newton over ampere times meter. Now we have two orientations, of course. If the wire or the current is perpendicular to the magnetic field, the magnetic force would be maximum because sine theta would be sine 90, and sine 90 is 1. So here the angle is between the field and the current, or the wire. If the wire is parallel to the magnetic field, then there would be no magnetic force acting on this wire because sine 0 will be 0, so magnetic force will be equal to 0. Let us talk about parallel wires that are carrying a current near each other. Let's have the two wires. One of them is a red wire and the other one is a blue wire. That is the second case. The first one, let us have the currents in the same direction. And when we have currents in the same direction, the force between these two wires will be attractive. So they will be attracting each other. If we look at the forces, they are toward each other, so they are attracting each other, and they have the same magnitude, but they have opposite direction. Although it is attractive, it is still opposite direction. So don't confuse opposite direction with the attraction and repulsion, please. For the second one, let's have the currents in the opposite direction. Since the currents are in the opposite direction, the force between them would be repulsive, so they will be repelling each other. Again, they have the same magnitude and they have opposite direction, and the forces will be moving away from each other. They are still opposite to each other, but they are away from each other. In both cases, both forces are acting on different objects. That's why they don't cancel each other. But why do we have this attraction and repulsion? What is the reason behind it? Let's explain that one. Let us have two wires again, and one that is red and the other one that is blue. And each one is carrying a current up to the page, so the currents are in the same direction. The red wire has a magnetic field around it. So at the right side of the red wire, the magnetic field is into the page. At the left side, the magnetic field would be out of the page. For the blue wire, the magnetic field, again, at the right side will be into the page, and at the left side, it would be out of the page. Now let us bring these two together. Now, as you see, they are in each other's magnetic field. So they are both wires that are carrying a current inside an external magnetic field. If we look at the red wire alone right now, it is carrying a current perpendicular to a magnetic field, which is the magnetic field of the blue wire. So there will be a magnetic force acting on the red wire, and the magnetic force can be found by BIL. If you remember, we said that B is always the external, I and L are the wire itself. So magnetic force acting on wire 1, I1, L1, but B is always external. Let's copy this to the other side and change the reds to blue and blues to red. So the blue wire right now is carrying a current inside an external field, which is the magnetic field of the red wire. So there will be a magnetic force acting on it, and magnetic force acting on the second wire would be equal to BIL. I will be 2, L will be 2, but B is external, which is the other wire's magnetic field B1. These two forces are always action-reaction pairs, and F1 is always equal to minus F2. Please remember that if you increase any of the currents, both forces will increase at the same time, because if you increase one current, the magnetic field of that current will increase, which is available in the other wire's magnetic forces equation, and they are always opposite in direction, and they are always equal in magnitude. So if I increase both currents twice, both magnetic forces will increase by 4 times. Magnetic force acting on a current carrying wire has 3 applications. The first one is a device that's called as galvanometer. The second one is a device that we use it in our daily life, which is the loudspeaker or any speaker. And the third one is a very useful medical device, which is called as MRI. First, let's talk about the galvanometer. Galvanometer is a device that is used to measure very low current. By very low current, we mean microampere and milliampere. And this is the diagram of a galvanometer. The first one is a coil. The second one is a permanent magnet. We have a scale here, and the scale has a 0 in the middle, positive on the right side and negative on the left. And we have a needle to measure the current. And we have a soft iron here to increase the efficiency. Since the coil is carrying a current inside a magnetic field, there will be a magnetic force acting on it. Let's say that the magnetic field is to the right side, which is from north to south, and let us have a current that moves like this in the segment of the coil. If we use the right hand rule, we will be able to find the magnetic force, which will be downward. Since this is the axis and the force is applied from a distance to the axis of rotation and it is perpendicular, there will be a torque acting on this coil, so it will rotate. So we can say that whenever there is a current in the galvanometer, there will be a magnetic force acting on the coil. Because of the magnetic force that is applied at a distance, there will be a torque acting on the coil, and it will rotate the coil and the needle together because they are connected. It will rotate until an angle of theta. If we increase the current, magnetic force will increase, the torque will also increase, and the needle will rotate to a greater angle. That's how it will rate current, and vice versa. If you decrease the current, all of them will decrease, so it will rate a lower value. But what happens if I reverse the direction of the current? If the direction of the current is reversed, the magnetic force will be reversed, the torque will also be reversed, and the angle will also be reversed, so it will deflect to the negative side. Galvanometer is used in the construction of both ammeter and voltmeter. Ammeter is a device that is used to measure current. Voltmeter is a device that is used to measure potential difference. First one, let's talk about converting galvanometer into ammeter. Actually, the explanation that we will do in a moment is not just for galvanometer into ammeter. We can also have an ammeter that measures a very low current, and we can still convert it in the same way to an ammeter that can measure very high current. Let's have a galvanometer. Let's say that this galvanometer or ammeter can measure up to 1 ampere. It has a resistance of 3 ohm. So this is Ig and this is Rg. We need to be able to measure up to 10 ampere. So what can we do? This galvanometer cannot take this 10 ampere. So we have to divide this current. To divide the current, we need to connect a resistor to this galvanometer. But we need to connect the resistor in parallel combination, because only in parallel the current is divided. So if I connect this resistor in series combination, I think the 10 ampere will pass through both of them and it will try the ammeter or the galvanometer. So we need to connect it in parallel so that the current is divided. So this is parallel combination. Now the second problem is that we need to make sure that only 1 ampere passes through the galvanometer, and this resistor should be able to take up to 9 ampere. Otherwise, if it takes 8 ampere, 2 ampere will pass through and try the galvanometer. So we need to make sure that this 9 ampere will go through the galvanometer. Let's remember the Ohm's law. R will be equal to V over I. So as current increases, R must decrease. So we need to use a very low resistance because we have a very high current, and this very low resistance has a special name which is called as shunt. So this is I shunt and this is IG. So we can say that I shunt is equal to I total minus IG. So this is also R shunt. Whenever we see parallel, we need to always remember that potential difference is same. So V is same in both the shunt and the galvanometer or the ammeter. So we can say that Vg is equal to V shunt. Every V is equal to IR from Ohm's law. So both are equal to IR. The left side is IGRG, the right side is I shunt R shunt, and that is our equation in the conversion of galvanometer or low current ammeter to a high current ammeter. Now let us convert a galvanometer into a voltmeter. Or we have a voltmeter that measures very low potential difference. We can still convert it to a voltmeter that measures high potential difference by the same way. Let's have a galvanometer or a voltmeter that measures up to 10 volts and has an internal resistance of 100 ohm. And we have potential difference that we want to measure that is 50 volts. This is the total one. So we need to divide this 50 volts so that only 10 volt goes to the galvanometer. How can we divide it? Of course, again, by connecting a resistor, but this time the resistor must be connected in series combination because only and only in series combination potential difference is divided. Now we need to make sure that 40 volt goes to this resistor and only 10 volt goes to the galvanometer. How can we make sure most of the potential difference goes to the resistor? And we can find this by looking at the Ohm's law. And according to Ohm's law, as resistance increases, potential difference also increases. Since I need a high voltage, the resistance of the resistor must be very high. And we can say that VR is equal to V total minus VG. And here we have series combination. And we need to remember that whenever we see series combination, current is same in all components. So we can say that IG is equal to IR. And every current according to Ohm's law is equal to V over R. This side is VG over RG and the other side is just VR over R. Loudspeaker is a device that uses a magnetic force acting on a coil inside the magnetic field. So at the beginning we have sound which is converted into a varying electrical signal by a device which is called as microphone. So microphone is converting sound which is a mechanical energy into a varying electrical signal which is electrical energy, and the conversion of mechanical to electrical energy is done by microphone. But loudspeaker will be doing the opposite. Loudspeaker is converting electrical energy into mechanical energy, and the sound that we have has a frequency which will be converted into a current by the microphone that has the same frequency. So the frequency of the produced current is same as the frequency of the mechanical sound, and this is a very low current, so we need to send it into an amplifier before sending it to a speaker. Amplifier will increase current without disturbing the signal, and the amplifier will send this varying electrical signal or electrical current to a loudspeaker. In the loudspeaker we have a varying electrical current that has a frequency which will cause a force that will be varying too. So the force will be right and left. This is the varying magnetic force. Since the magnetic force is always changing, it will cause the paper cone to move back and forth. So the paper cone will move back and forth. So the same sound will be produced that was at the beginning. And remember that mechanical energy is converted into electrical energy by the microphone, but loudspeaker is converting electrical energy into mechanical energy. So loudspeaker converts electrical energy into mechanical energy.